Welcome to your AP Statistics video for Chapter 13, Experiments and Observational Studies. This is video 1 of 2. Okay, so let's define some things. What is an observational study? An observational study is a study where researchers don't assign choices, they simply observe them. In other words, they just watch what people do. A good example of this is music and grades. There's a study done that noticed that students who were involved in music, band, or orchestra tended to have better grades than students who were not involved in music, band, or orchestra. And the researchers just simply chose the people to be part of their study and then observed what their involvement in music was and also what their grades were. There's two types. There's retrospective and prospective. Retrospective, that would be if the people, say, involved in the music and grades study selected a group of young people and then looked at their past music involvement and their past grades. A prospective study would be if the same researchers chose a group of students and then from that point on monitored their music involvement and their grades. So retrospective looks back, prospective watches as we move forward. The value of observational studies is they are excellent for finding patterns and discovering trends. The limit is you cannot determine cause and effect. Okay, back to the music and grades study. It could be that smarter people are attracted to music and so tend to have better grades. Or it could be that involvement in music makes you smarter and gives you good grades. We can't tell based on an observational study alone. If you want to determine cause and effect, you need to do an experiment. So what is an experiment? Well, like I just said, it's a study designed to prove a cause and effect relationship. The experimenter has to identify at least one explanatory variable called a factor to manipulate. So in the music and grades example, the factor would be music, and they could actually come up with different what we call levels of music. And so you might have students involved 1 day a week in music, 3 days a week in music, and then 5 days or more a week in music. And at least one response variable to measure, and that would be grades. An experiment manipulates factors to create treatments. Like I said, you actually figure out exactly how much exposure to music a student is going to receive, and then randomly assign subjects to these treatment levels. So you would take a group of students and randomly assign them to probably have one group where they had no exposure to music, 1 day a week of music, 3 days a week of music, 5 days a week of music. And the reason you randomly assign them is to take care of the case. Remember I said just a minute ago that it could be that smarter people are attracted to music programs. Well, you want to take that out of the experiment. Okay, so what you do is you randomly assign the subjects to the different levels of music exposure. And then you would compare the responses of the subject groups across the treatment levels. So, every 6 months, say for 3 years, you would compare the grades of the different groups. In general, the individuals on whom or which we experiment are called experimental units. So if we're studying plants, if we're studying dogs, if we're studying, anything that's not human, we call them experimental units. Humans don't really like to be referred to as an experimental unit, and also because of ethical reasons, it's very important that the people conducting the experiment are mindful that they are actually working with humans. They're called subjects or participants. The specific values that the experimenter chooses for a factor are called the levels of the experiment. Again, going back to our music example, the levels would be no music lessons a week, 1 music lesson a week, 3 music lessons a week, or 5 music lessons a week. A treatment is a combination of specific levels from all the treatments that an experimental unit receives. Well, in our example, there's only one factor. So that factor, the levels of that factor are the treatments. But let's say we wanted to know if involvement in sports had a similar effect, or some combination of music and sports was like the perfect combination of involving the arts and the physical part of our beings to produce good academics. And then you might have the levels of music that we had, none, 1 time a week, 3 times a week, 5 times a week, and have similar levels of athletic involvement. And so you would then look at all the possible combinations, and that would give you your treatments. There are 4 principles of experimental design. The first one is control, and by control, this means we want to control the sources of variation that might cause changes in the response, and we control the known sources of variation other than the factors we're testing by making conditions as similar as possible for all treatment groups. For instance, back on our music example, you would not want the group that, say, had music 5 times a week to also be part of some special academic program that the other treatment groups, 0 times a week, 1 times a week, 3 times a week, weren't involved in, because if that group with the 5 music lessons a week does better, we would not know whether that was due to their involvement in the academic program or their involvement in the 5 music lessons a week. So we want to control for any sources of variation that we know of. Now, sometimes there are sources of variation that we don't know about, and that's where randomization comes in. It actually helps support this idea of control. Random assignment of subjects to treatments allows us to equalize the effects of unknown or uncontrollable sources of variation. Sometimes we know the sources of variation, but we just can't control them. And other times we don't know sources of variation, and the randomization takes care of that. It does not eliminate the effects of these sources, but it spreads them out across all the treatment levels, so we can see past them. They're working equally among all the different treatment groups, so their effect is going to be present across all of them, and so one group does not have an advantage over the other, or disadvantage under the other. And without randomization, you do not have a valid experiment. Replication. Now, there's a couple of meanings of replication as far as experiments go. What we mean by replication here is that you repeat the experiment applying the treatments to a number of subjects. You can't just have one person in each of your treatment groups or one plant in each of your treatment groups. You have to have multiple individuals in each treatment group. The outcome of an experiment on a single subject is an anecdote. It's not data. Okay, it just gives you a nice story. It might be suggestive of what you might want to look at in a future experiment, but you have, in order for you to have something meaningful in the scientific community, you have to see a result with a number of subjects. The 4th principle is actually an optional principle. Sometimes it's used, sometimes it's not, and that is blocking, or the use of or to block for an experiment. We block when there is an attribute of the experimental units that we're not actually studying and we can't control, but that we suspect will affect the outcomes, the responses of an experiment. Okay, sometimes randomization, although it's going to take care of this to an extent, is not enough control, and we have a good reason to believe that a particular attribute, let's say we felt like there was going to be a difference in males and females in their grades. Let's say we thought one gender was going to have slightly higher grades than the other regardless of their music involvement. Then what we would want to do is block according to gender. Okay? If we group similar individuals together and then randomize within each of these blocks, okay, we don't randomly assign gender to people. We separate out our volunteers for our study into male and female, and then randomly assign an equal number of males to no music lessons a week, 1 music lesson a week, 3 music lessons a week, 5 music lessons a week, and then we do the same thing within the females. We can remove much of the variability to the differences among the blocks. Okay, so if maleness and femaleness has an effect on grades, we remove that by studying males and females separately. What we don't want, if we really believe there's going to be an advantage to one gender or the other as far as grades are concerned, what we don't want is, through randomization, to end up with a large number of one gender and a small number of the other gender in any one treatment group. Because what we would be measuring then, we would not be able to tell whether it was the gender effect or whether it's the music effect on grades. Blocking is an incredibly important compromise between randomization and control, but unlike the first three principles, it is not required in an experimental design. Okay? In fact, you kind of have to justify your use of blocking. You have to be able to have some sort of explanation of why you think the variable according to which you blocked has an effect on the responses. For experiments, we could either describe in lengthy paragraphs or we could diagram them to plan our experiment and also to communicate what we've done. Diagrams are going to be the method that we choose. They emphasize the random allocation of subjects to treatment groups, the separate treatments applied to these groups, and then the ultimate comparison of responses. If we block, it also brings that in. So you can see it really helps us demonstrate that we are using those principles of experimental design. Now, when we're looking at when we make our comparison, if there's a difference, we want to know, does that difference make a difference? Is it a big enough difference that anybody really cares? Is it a big enough difference that we have shown that our different treatment groups have a different response, and that it's due to the treatments themselves? So how large does that difference need to be for us to say that? They have to be large enough that we believe we did not get the difference results just due to chance alone, just due to, you have slightly different individuals in the different groups. When that happens, we call it the result statistically significant. That's what we're looking for. Now, we're not going to really define what makes something statistically significant right now. The main thing is you just need to have this concept developing that the differences are larger than what we would get from chance alone. Okay, now, we use some of the same language with experiments and surveys and samples, but we need to make sure we understand the difference in the purposes and how that affects the differences in how we use randomization. Sample surveys randomly select sample members to get a representative sample because their purpose, the sample survey's purpose, is to estimate population parameters. Remember, from our sample, we get a statistic that is an estimate of the population parameter, and for that to be a good estimate, our sample has to be a representative microcosm of the larger population. For experiments, they randomly assign subjects to treatments because their purpose is to try to assess the effects of treatments on responses, assessing a causal relationship. We want to be able to establish that the treatment caused a certain response. So that's where we randomly assign. If you wanted to then be able to apply the results of your experiment to a larger population, you would need to actually do two steps of randomization. You would need to randomly select the people who were going to be involved in your experiment, and then you would need to be able to randomly assign them to their treatments. That's often very difficult. Usually for experiments, you're relying on volunteers, and so you're able to show the cause and effect, but you have limits to being able to then apply your results to a larger population. Okay, control treatments. Often we want to compare a situation involving a specific treatment to the status quo situation. If you are doing an experiment on a new migraine medication, instead of leaving people without any migraine medication, what you might do is for a control group, instead of saying, okay, no migraine medicine for you, perhaps you use the most commonly prescribed migraine medication to give you a baseline. This baseline business as usual measurement is called a control treatment, and the experimental units or participants to whom it is applied are called the control group. When we know what treatment was assigned, it's difficult not to let the knowledge influence our assessment of the response, even when we try to be careful. Just subconsciously, if we really believe that a particular treatment is going to be the best case scenario, it's very hard for us, either as the person who's participating in the study, not to think, oh yeah, I really do feel better. I'm taking this new migraine medicine. No, my head feels fine. or if we're the evaluator. Oh, this person's not quite sure whether they had a migraine or not on that day. Oh, look, they had the new drug. Nah, they didn't have a migraine on that day. You know, not that we would consciously do that necessarily, but subconsciously we tend to do that. If you tend to be a skeptic, maybe you would go in the other direction. But in order to avoid all of this, we employ something called blinding. That's to avoid this bias that results from knowing what treatment was assigned. That's the whole purpose of blinding. So there's two main classes of individuals who can affect the outcome of an experiment. It's important you know this, because if you're going to decide whether or not an experiment can be blinded, you need to know which group can be blinded or if both groups can be blinded. The first is those who can influence the results. So that's the subjects, the people who are actually using the treatment or undergoing the treatment administrators, the technicians who are actually in there when the treatment's being applied. And then those who evaluate the results, the judgments, the treating physicians, etc., the people who are deciding what the responses actually are. Now, someone has to know. There is somebody who is overall in charge of the experiment, or who's been assigned this job by the person who's in charge, who has what's called the key to the experiment, who knows which subjects received which treatment. And eventually that has to be made known in the analysis. But during the course of the experiment, it is absolutely possible for many experiments to be conducted in a way that neither one of these groups, the influencers or the evaluators, know which subject is receiving which treatment. When all individuals in either one of these classes are blinded, an experiment is said to be single blind. Now, back to our music example, the subjects, the music teachers are going to be aware, those who are influencing the results are going to be aware whether somebody's coming to music class once a week, no times a week, 3 times a week, or 5 times a week. So we would not be able to blind that group. The teachers who are assigning grades to the students may not know, okay, especially if the music lessons aren't part of the normal class day. The teachers would not necessarily need to know who's taking music class and who's not. So in this case, this experiment could be single blind. When everyone in both classes is blinded, the experiment is called double blind. So back to the migraine medication, if the new migraine medication looked exactly like the old migraine medication, then there's no reason why the people who are taking the pills would need to know which pill they were taking, nor would the people who are actually evaluating the results. Okay, in that case, you could do double blind. Placebos. Okay, now, if you felt like it was ethical to totally let the poor migraine people not have any kind of treatment at all, sometimes it's good to throw in a sham treatment just to see if the fact that the person is receiving any treatment at all is making them feel better. Okay. Often simply applying any treatment can induce an improvement. To separate out these effects, we can use a control treatment that just mimics the treatment itself. A fake treatment that looks just like the treatment being tested is called a placebo. And they are the best way to blind subjects from knowing whether or not they're receiving a treatment, because you can make the placebo seem just like an active treatment. So, for instance, in the migraine example, if you deemed it ethical to let people, just suffer from the migraines and just have a placebo, instead of using the current treatment for migraines, you might just use a pill, often called a sugar pill, because the only thing in it are, quote unquote, sugars, things that will have no effect. You would give the people just an ineffective pill that looks just like the treatment pills, but that would be a placebo. And this is called the placebo effect. It occurs when taking the sham treatment results in a change in the response variable. This highlights both the importance of effective blinding and the importance of comparing treatments with a control. Okay, we are going to want comparison in all of our experiments. So the best experiments, and this is critical for you to know, are usually randomized. So there's random allocation of subjects to treatments. They're comparative. You have to have more than one group. If at all possible, it's great for them to be double-blind and placebo-controlled. Okay, that's going to be it for video 1. And then we are going to come back with video 2 and finish out this chapter and give you some examples.